Hi, I'm Ryan Baker, and this is Big Data in Education. Today we'll be discussing logistic knowledge tracing and one of its earliest formulations, performance factors analysis. Logistic knowledge tracing is a broad framework for knowledge tracing models based on logistic regression formulas. The first member of the LKT family that ran in real time was performance factors analysis. PFA measures how much latent skill a student has while they're learning, but expresses it in terms of probability of correctness the next time the skill is encountered. Within PFA, unlike BKT, there's no direct expression of the amount of latent skill except that probability of correctness. And that, by the way, is true of the entire LKT family. So what's the typical use of PFA? To assess a student's knowledge of topic X based on a sequence of items that are dichotomously scored. In other words, the student can get a score of 0 or 1 on each item, where the student can learn on each item due to a variety of things: help, feedback, scaffolding, and so on.
How does PFA differ from BKT? Well, let's talk about its key assumptions. First of all, each item may involve multiple latent skills or knowledge components. This is a big difference from BKT. In BKT, there's the assumption that there's only one skill per item, and that means that you can only really use BKT in situations where you've designed the curriculum so there's really only kind of one relevant skill, one skill with a chance of being hard at any given time. PFA doesn't make this assumption, and so it can be used a little more widely. Also in PFA, each skill has a success learning rate, gamma, and a failure learning rate, rho. And that's different from BKT, where the learning rate's the same, success or failure. In fact, these success and failure learning rates take into account not just learning, but also they take into account what it means that you've failed or succeeded. So they take into account that you failed or succeeded, as well as the learning based on those cases. PFA also has a difficulty parameter beta, but its semantics can vary. More on this later. From these parameters and the number of successes and failures the student has had on each relevant skill so far, we can compute the probability, P of M, that the learner will get the item correct. So PFA can be expressed mathematically as follows. First you compute M. M is a function of beta, the difficulty, and the sum of the number of successes and failures with their weight parameters, gamma and rho, that students have had on every relevant skill in the problem. You take that M and then you put it through an exponential function. So let's look at an example. We'll start first with a reasonable example. We'll move on to crazy examples later. Let's say that you have gamma of 0.2, rho of 0.1. So we're assuming that you improve your future performance double if you get success compared to if you get a failure. And beta is negative 0.5, which means the item's a little hard. So the initial M, there's no successes or failures yet, is going to be negative 0.5. That's the beta. So the probability the student will get it right on the first attempt is 0.38. At this point, we have no information about the student. It's like L0 in BKT. And in fact, let's say the student gets it wrong. Now we update for the next opportunity M. We take that negative 0.5, item difficulty is the same here. We haven't really talked about this yet. And we add, for that failure, 0.1, the rho, times 1 failure so far. And this gives us negative 0.5 plus 0.1, which gives us negative 0.4. So we say the probability they'll get it right is 0.4. Even though they got it wrong, we're saying they still learned more than the evidence of them being wrong told us they won't get it. And in fact, let's say the actual 0. In this case now, the M will be negative 0.5 plus 0.1 times 2. We've got 2 failures now that are weighted 0.1 for rho. Negative 0.3 is the result, which gives us a P of M of 0.43, and the actual is 1, let's say. So now they have 2 failures and 1 success. So now the function is just a little more complex. It's negative 0.5, the beta, plus 2 failures, 1 success, which gives us a probability of M of 0.48. And you can see it's kind of just going up over time.
Now, as in BKT, PFA can have degenerate models. And Maier et al. 2021 talk about 3 degenerate cases that you can get, where gamma is less than 0, where gamma is less than rho, and where both gamma and rho equal 0. There's also a seemingly degenerate case that actually isn't, where rho is greater than 0. And Maier and her colleagues talk about this, that in this 4th case, there's actually not degeneracy because of the multiple functions the parameters perform in PFA. In this specific case, what might be happening is that the rate of learning the skill might be bigger than the evidence of lack of student knowledge that an incorrect answer provides. So even though rho greater than 0, you get better when you get it wrong, seems implausible it actually isn't necessarily degenerate for that reason, as long as the improvement associated with getting it right, gamma, is greater than the probability associated with getting it wrong, rho. So let's take an example of that first degenerate case where gamma is less than 0, which means that if you get it right, your predicted future performance is worse. This student here got it wrong the first 2 times, and their predicted performance drops. We should expect that. But then they get it right the 3rd time, and their predicted performance still drops, from a predicted performance of 18% correct to 17% correct. Now the drop's not as extreme for right as wrong, but still they get it right and the system thinks they're doing worse, and this is degenerate within the PFA framework. Here's an example of degeneracy case 2. In this case, rho is greater than gamma, which means you get better if you get it wrong than if you get it right. And what you can see here is the student gets it wrong a couple times, and their probability of getting it right on the next one goes up more than when they get it right. Another thing to note, values of rho below 0 don't actually mean negative learning. It's not like the student is actually unlearning. What they mean is that the failure provides more evidence on a student's lack of knowledge than the learning opportunity causes improvement. And that's why it's not degenerate to have rho above 0. So how do you address degeneracy? There's a simple approach in Maier et al., which is you bound rho and gamma. And just like BKT, that doesn't reduce model performance substantially, at least in that paper's data. Now, what causes degeneracy? We'll come back to this in a minute.
So, parameters in PFA combine information from correctness with improvement from practice improvement. And this makes PFA models a little harder to interpret than BKT. Nothing wrong with it, just you have to think a little more deeply. So how about adjusting beta? Let's say if you adjust beta. If you look at this case, we got that beta of negative 0.5. You saw this pattern before. If we change it to negative 1.5, the same kind of amount of improvement happens, but they start from a lower baseline. And if we set beta to +3, then it starts with a really high baseline. From the very start, we assume a student's going to be 95.3% correct. Incidentally, if we think a student's going to be 95.3% correct, it probably is relatively unlikely that you want to give the student this item to study unless there's some really good other pedagogical reason. For example, to help them kind of solidify their knowledge, although that's an issue for attention, for memory strength. That's something we'll talk about later in the week. That's not a case where you really want to use PFA or BKT. Or maybe it's just a step that you kind of have to do in getting to another step, and it's just too much of a pain to design something that skips it. For example, entering a given in a worksheet. It may not be worth actually letting the student skip that step. So for beta parameters, Pavlik proposes 3 different beta parameters: item, item type, and skill. And so is the difficulty something that each item has a difficulty? Is the difficulty something that each skill has a difficulty? Or are there kind of types of items somewhere in between? These 3 approaches result in different numbers of parameters and greater or lesser potential concern about overfitting. The more parameters, the more risk of overfitting.
And a minute ago, you might have asked, what causes degeneracy? Well, beta is a big part of what causes degeneracy in PFA and, for that matter, LKT in general. If beta is used at the skill or item type level, and the learning system moves students from easier to harder items within a skill, then you're going to get gamma being less than 0, because the system's actually quietly assigning harder items over the time. Also, if items are tagged with multiple skills, then shared variance, aka collinearity, between skills could produce degenerate parameters.
So how do we fit PFA? Unlike BKT, where there's several alternatives that people consider, typically for PFA, just expectation maximization is used.
It's pretty simple. First, we start with initial values for each parameter, which are typically arbitrary. We then estimate student correctness at each problem step or item based on those values. We then re-estimate the parameters using the student correctness estimate. And if the goodness of the model is substantially better than the last time it was estimated, and we haven't reached some pre-chosen threshold for the maximum number of iterations we can do, we go back to step 2. We re-estimate student correctness from the parameters, we re-estimate params from the student correctness, go back to step 2, and keep going until you kind of don't get any better, or you get to a point where you've gone through your maximum number of tries. EM is vulnerable to local minima, which means that sometimes you get to a parameter space where there's actually a much better one over somewhere else, but you can't get to it from where you are. And to try to avoid that, randomized restart is typically used.
So is PFA better than BKT? Actually, it turns out that they have approximately equal predictive power across a lot of studies. all done, as you can see, about 7 years ago. There's different virtues and flaws for the two algorithms, so choose the one that better fits your goals.
Second key question, is PFA actually used in the real world? The answer is yes, but far less often than BKT. Maier et al., for example, discuss its use in Reveal Math 1. But compared to BKT, which is used in dozens of systems, PFA is a relatively uncommon algorithm. One issue in the real-world use of PFA is in how it handles rare skills, which can impact model inferences on common skills as well. Because PFA is typically used in cases with items tagged to multiple skills. Ironically, some of the packages for PFA can't handle that, but that's the main benefit that PFA has over BKT. And when you have an item tagged to multiple skills, a rare skill is going to impact the common skills it intersects with. Maier et al. Handled this by creating a catch-all skill for rare skills, and they found that using average parameters from all the common skills also works. So some final thoughts on PFA. PFA is a competitor for measuring student skill, which predicts the probability of correctness rather than latent knowledge. It can handle multiple cases for the same item in a graceful way, which is a big virtue. Going beyond PFA. An early major extension to PFA was PFA decay by Yue Gong and her colleagues. PFA decay weights actions further back in order less strongly, and it adds an evidence decay parameter, sigma, substituting an equation that uses that evidence decay for the previous summation. Is it any better? Not really. Historically important, people don't use it today. A next extension was RPFA by Galliard and Golden. RPFA also weights actions further back in order less strongly. What it does is it looks at the proportion of success and failure weighting by the distance in order from the current action. It adds an evidence decay parameter B, and in order to make the math work, it turns out if you don't do this, the math doesn't work. It adds what are called ghost practices before the current practices to make the math work. It substitutes a much more complex equation for the previous summation, and again, doesn't get that big a difference over original PFA. Building on this and some other work that had been going on in his lab at the time, Phil Pavlik and his colleagues created a general framework for variance of PFA. And here's a table. You can see a lot of variance. There's a lot of things you can do to modify PFA. The biggest contribution that LKT probably made was that new and ongoing work on variance to PFA now typically frame themselves in terms of LKT components and propose additional components. What it did was, instead of getting people in a space where every single little tweak to PFA became a new named algorithm, now we can just say LKT components 8 and 10. Work continues on PFA. Next up, we're going to discuss item response theory, a classic approach with some limitations that BKT and PFA don't have.